Alright, welcome to this session. In this particular kind of a video, I just want to clarify a few things. For those that were available during the physical class, I think there was quite a confusion here, and I just want to put emphasis on how you're supposed to find the quantum numbers of different kind of elements. I think it's quite easy for you to comprehend exactly what we're supposed to talk about here. So in finding the quantum numbers that are available here, the first thing that we did was to find out, okay, what is the electronic configuration of such kind of an element as beryllium? Knowing that the total number of electrons that are here are 4. Alright, this is what we discussed. To say the total number of electrons that are here are 4. Because we know that this 4 here is coming from the proton number or the atomic number of the beryllium atom. So this is the atomic number. After collecting the atomic number, we want to make sure even as we start collecting these electronic configurations, we're going to collect them based on the orbitals. Mean that we're supposed to start from the s orbital, and then we're starting from the s orbital, moving from the 2 orbital, knowing that the s orbital will occupy a maximum number of 2 electrons, and the p orbit will occupy a maximum number of 6 electrons, the d orbit occupying a maximum number of 10 electrons, and the f orbit occupying a maximum number of what? Of 14 electrons. So if I start from here, I'm going to have my 1s. This 1s, the s will occupy the maximum number of 2 electrons. Secondly, after the 1s from this position, we're going to move on to the 2s. The 2s will occupy a maximum number of how many electrons? 2 number of electrons. So there is a 2. There we have it. And then the second part of the question they were asking us to find or to collect a set of quantum numbers for the orbit occupying the highest amount of energy. So for the orbit occupying the highest amount of energy, we said that is going to come from the first orbital, which is the 1s2 orbital. Why did we make that assumption, or why did we make that conclusion? In fact, this is not an assumption, but it is a conclusion. We know that in an element, the center of that element or the center of that atom, we have what we're calling the nucleus. And the nucleus, that is where we have much of the energy. So in the first part of the shell, we have the principal quantum number being equal to 1, and the second part of the element where you have the principal quantum number being equal to 2. If the principal quantum number is equal to 1, it means that the n equal to 1 has the highest amount of energy because it is being close to the nucleus. And the more the shell is going away from the nucleus, like where you have the principal quantum number here being equal to 2, it means that you have lower energy. In the third one also, when you draw like that, you're going to have n equal to n equal being to 3, and when n is equal to 3, that equal implies that the amount of energy begins to decrease because we're moving away from the nucleus. That can be proved by looking at the energy of an orbital when n is equal to 1, when n is equal to 2, and when n is equal to 3, by looking at the formula negative b over n squared, where the n is representing the shell number, which is n is equal to 1, or the principal quantum number. So when you find out like that b is a constant, that number will give you a full description on the energy levels that are existing at each respective shell. So you discover to say n is equal to 1, it has the highest amount of energy, and therefore at that particular point in time it is very unstable. So now, since I've given that analysis here, we have our electronic configuration of beryllium as 1s2, 2s2, meaning that if I add the 2 plus 2, I'm going to have 4 as the maximum number of electrons, which should be equal to that. That should be the target. After doing that, now let's find out, okay, now we have this. What are the quantum numbers that we're supposed to get? So for the quantum numbers we're supposed to get, I'm going to use, this is 1s2, where I have my principal quantum number here being equal to what? Being equal to 1. The principal quantum number is equal to 1, the first one that we have there before the s orbital. That's the principal quantum number. And after the principal quantum number, we're supposed to get what we're calling the angular quantum number, which is L. The angular quantum number, you can get it by saying this is n, and n minus 1 can give us the formula for the angular quantum number. If we say, okay, what's the value of n there? It is a 1. And then you say minus 1. We're going to say the angular quantum number is being equal to 0. And then remember, in different respective orbitals, you can have the s orbital, you can have the p orbital, you can have the d orbital, you can also have the f orbital. The value of L, or the angular momentum quantum number in the s orbital is equal to 0. The p orbital 1, the d orbital 2, the f orbital 3. So you have the respective values of the angular quantum numbers at each respective orbital. The s orbital 0, the p orbital 1, the d orbital 2, and the f orbital being equal to 3. So you can see that it's aligning here. The angular momentum quantum number here, when we say n minus 1, where the n is a 1, minus 1 is going to give us a 0. And here, when you make that assumption, it's going to give us a 0. So now we found out the principal quantum number here is equal to 1. The angular momentum number here is equal to 0. Good. Then we're supposed to find what we're calling the magnetic quantum number, which is the ML. How do we get the magnetic quantum number? It lies between the negative value of the angular momentum number being less or equal to the positive value of the angular momentum number. So even the magnetic quantum number here is equal to what? It is equal to 0, because basically what is lying here is just the 0. So you have the angular momentum quantum number being equal to 0, the magnetic quantum number being equal to 0, and then the last thing is the spin. Now I want you to get me very clearly on the spin, or the ms. The ms. So now at ms, one thing that we're supposed to understand here is that when the L, or the orbital angular momentum quantum number, is 0, it's corresponding to the s orbital, this one here. Alright? So this is the spin, or the magnetic spin. Alright? So I'm saying when L is equal to 0, it is corresponding to the s orbital, because we know that the s orbital there, it is also equal to what? To 0. So for an s orbital, the possible spin values are determined by the spin quantum numbers, okay, which can either be a positive, like we discussed, that the spin numbers, or the spin quantum numbers, can either be a positive 1 over 2 or a negative 1 over 2. So in other words, an electron in an s orbital can have a spin of a positive 1 over 2 or a negative 1 over 2. So these are the spins that we're supposed to get in that particular answer. So these are what we're calling the spin quantum numbers. So from the beryllium atom, we have the angular quantum number equal to 0, the principal quantum number being equal to 1, and the spin quantum numbers being equal to a positive 1 over 2 or a negative 1 over 2. Because why? In the s orbital, how many number of electrons are we having? Only 2. The positive one, and we only have 2 number of electrons. So we're going to have 1 up, 1 down. So positive 1 over 2. And then down we're going to have negative 1 over 2. So I want you to get this very clearly. In other words, an electron in an s orbital can either have a positive 1 over 2 or a negative 1 over 2, meaning going downwards, that's a negative spin, going upwards, that is a positive spin. I hope this really puts an end to all the confusion that we had in today's class. So thank you so much for watching this video, and I wish you the best of luck in your quiz.